Hey there, and welcome to another edition of the Walton Engineering Podcast. I'm your host, Mr. Benton. Today we talk about an inclined plane wrapped helically around an axis. Let's get started. Please follow these tips for a more efficient video viewing experience. Here's what I hope you'll understand after watching this video. You've heard on Big Bang Theory, an inclined plane helically wrapped around a center axis. And I think Sheldon actually talks about that one. But a screw has two components. It's really an inclined plane wrapped around a cylinder, and then we use a wheel and axle to create that rotary motion. And a screw is one of the simple machines that converts rotary motion into linear travel. Think about that. As the screw wraps, as we turn this, it actually moves the screw linearly. Okay, so we create rotary motion, and the screw moves linearly. So what are the properties? It changes rotary motion into linear motion. It is definitely a threaded fastener. We want to fasten things together by using a screw. And this could be bolts, as you guys will use in the used in the gear activity. It could be screws where we're actually screwing two pieces of wood together. It has a very large mechanical advantage. Very large mechanical advantage. We'll see in an example in a few minutes. But it also has a large amount of friction loss. Well, part of that friction loss is what we want. We really want a lot of friction because that means that parts will stay together. If we didn't have much friction, then the screw might back out all by itself, or the nut might fall right off the bolt. And so it's a double-edged sword. We want the friction, but we also don't want the friction. The conundrum of an engineer. Well, let's talk about how we identify things in a screw. Okay, very important to understand what's going on so that we can then talk about the mechanical advantages that come out of using a screw. So we have this effort arm distance. All right, you're going to use a wrench. You're going to put it on top of this bolt, and we've got this distance from the center of the bolt out to one of the perpendicular edges. If we just put our fingers on there and twist, then that is our effort arm distance. Well, we might also put a wrench on there to increase that, so we're putting a lever on this. That adds a little bit more complication. So for right now, the effort arm is just this distance from the center of the bolt out to the edge of the bolt head. All right, we have this thing called pitch. And pitch is the distance between these threads. And what we do is measure it. We probably would use a caliper. You're right. We use a caliper. And as this bolt goes around one time, I'm going to move from here to here. And that's why it's called pitch. It's the distance that the screw would travel if I turned it around one complete time. One rotation would move the screw in this little bit, which is called the pitch. Now the diameter of the bolt, you can see what it is, just the diameter. Okay, we need to talk about threads. Well, we've got some thread information. You guys have seen this before. You've probably seen quarter 20 UNC as you were doing some of your IED stuff last year. So the diameter is kind of the first thing. This is a diameter of 1/2. We have threads per inch, and then we have some kind of description about the actual threads themselves. Are they coarse? Are they fine? Are they medium? Okay, so what this means is 13 threads per inch. Then the pitch is 1/13 of an inch. So I have 13 threads per inch. The pitch is 1/13 of an inch. So how many times would I have to rotate this screw in order to make the screw go 1 inch in? You're right. It's going to be 1/13 of an inch if I move around one time. If I move 13 times around, then this screw is going to go in one inch. Wow, that's a lot of work to get that screw to go not very far. But it's a huge mechanical advantage, which we'll see. All right, so what is the screw mechanical advantage? Here's a quarter 20 UNC. Okay, quarter means it's a 1/4 inch diameter. 20 is 20 threads per inch. So what's our pitch? Think about that. All right, the distance of the effort is 1 rotation of the effort arm. Well, what is the effort arm? Well, it's from here out to here, right? So that's the circumference of that. And what's the distance of the resistance? Well, it's the linear distance traveled during 1 rotation, or the pitch. Pitch. All right, the IMA then is the circumference. The circumference, distance of the effort is the circumference, divided by the pitch. The circumference over the pitch. So that's 2 pi times the radius of the effort, or 2 times the diameter of the bolt head, divided by the pitch. What's the AMA? Well, the AMA is the forces. So if I've got a 1200-pound resistance force and a 35-pound effort force, then I'm going to have a pretty high AMA. So what's the AMA of the screw? 34. Think about that. 1200 divided by 35, or 1200 divided by 30 is about 40, right? So you can pretty quickly see that 34 makes sense. What's the efficiency of the screw? What did we say the IMA was? Okay, the efficiency is 34 over 1,000. Oh my goodness. So the IMA of the screw was the distance of the effort over the distance of the resistance, or the the circumference over the pitch. So this efficiency is really bad. So what is that? About 3%. So really horrible efficiency, but what about that mechanical advantage? Pretty big compared to other simple machines. But think about this efficiency. Look at this. IMA is 1,000. The ideal mechanical advantage is 1,000. And by the time we get done with friction, we're at 34. Wow, what a loss. Really, really, really low efficiency. All right, lots of friction. All right, let's look at compound machines. Well, when we want to get the mechanical advantage of a compound machine, we just multiply the mechanical advantages of the different machines that are involved in this task.
We'll see you next time on the Walton Engineering Podcast. See ya.